Great. Well, I guess we'll get started. Welcome to everyone here and online. So today we have Thomas Klatzer, who is visiting us from Technical University of Graz. Thomas used to work at Siemens a little bit, I believe, and is currently doing his PhD in Graz, working with Sonia Vogren. Is it Vogren? Yeah.
Vogren, yeah. Yeah, people have a hard time pronouncing that.
I was guessing it was like a German Austrian pronunciation. But yeah, it's still tricky. So thanks for that. Yeah, Thomas is doing a lot of interesting work on a topic that is, I think, in all of our radars, it's coupling, big energy system model. So I'm looking forward to what you have to say on that. So Thomas, the floor is yours.
Thank you for the introduction, Emil. Welcome everyone. Welcome everyone online. My name is Thomas Klatzer. As mentioned, I am associated with Graz University of Technology and the Institute of Electricity, Economics and Energy Innovation. And I am visiting PhD here. And the core area of my PhD thesis is energy system modeling in the context of hydrogen. And today I want to present to you some of our preliminary results, which we wanted to write a paper about and then submit it to the IEEE General Meeting next year. And in this particular paper that we want to write, we are trying to assessing the impact of natural gas and hydrogen blending in energy system modeling. Okay, so what's on the agenda for today? First, I want to introduce you to the LEGO model that we are using and that I am extending. Then I want to give you some motivation about the hydrogen transition and why this is considered key by the European Union. Then coming to our main research question and the methodology that we apply. Followed by some case study results and a summary of the main takeaway to finish this presentation. So first, we're using the LEGO model. LEGO is an open source model, and I encourage you to go to GitHub and download the model and just give it a try and see if you can make use of it. LEGO is an expansion planning model, and it's based on the objective function of minimizing total system costs, and this includes the investments and operation costs. LEGO, for this paper, LEGO is run as a mixed integer program. At the moment, the model is still deterministic, and it covers a single year horizon. And its key features are that it's modular and flexible. LEGO is coded in GAMS, and its input data management, output data management is done with X. So what does modularity and flexibility mean? What do we understand by this? So there you can see that LEGO has a lot of modeling options, which you can include or omit from your framework, depending on the scope of your case study by just selecting a yes or no decision. So this includes, for example, including unit commitment constraints or omitting them, network as a single problem or as a DCOPF or an ACOPF approximation, so on and so forth. This covers modularity. In terms of flexibility, the model offers a very flexible temporal structure. So the temporal structure is represented by 3 different time indices. Chronological hours or periods. This means that we can model a full chronological time series, but we also have the option of considering representative days in this framework. The investment portfolio covers thermal units, renewables, and storage units. And here I want to point out that especially for storage units, we also represent long-term storages and short-term storages. And the representation of long-term storages in the key features of the model. And we also include some policy constraints which you can activate or omit, and it's very easy to add additional policy constraints to the model that might be interesting to you. And the thing that I am currently working on is including the natural gas and hydrogen sector to the model. So I've included gas infrastructure, for example, electrolyzer units and pipelines, and this key feature of today's talk, hydrogen and natural gas blending. As a motivation, why hydrogen is interesting for the European Union, and this blending idea is interesting. Actually, there is an association that's called the European Hydrogen Backbone Initiative, and they have come up with the idea and investigated the idea of setting up an European hydrogen transmission network. And they are considering repurposing of existing pipelines, but also setting up new dedicated hydrogen pipelines. In the future, like in the year 2050, this network could look something like this. And this association considers blending of hydrogen and natural gas very important, especially during the transitional phase in the 2030s, in order to have a suitable step and a stepstone towards a dedicated hydrogen network. And blending is actually permitted as of today. So as of today, you can blend up to 10% of hydrogen with natural gas. This is true for Austria, for example. And blending 10% of hydrogen in natural gas also does not affect the performance of end-use applications. So the gas plant can just be burned and it doesn't affect performance. However, in the literature that I've investigated in literature review, you can also check out this work, showed that there is a gap in terms of this blending idea. So there are holistic energy system models, and they either cover include natural gas systems or dedicated hydrogen systems and natural gas systems. And the way they do that is they assume that it's the year 2040 or 2050, and they say, okay, we have a dedicated hydrogen pipeline network. And we also have the option of setting this up in an investment program. However, this does not consider this transitional phase, and this is where blending comes into play. And there we found a clear literature gap, which we are trying to exploit with our work. So actually, the research question that we want to pose here is: does the formulation of natural gas and hydrogen blending have a significant impact on expansion planning decisions? And in order to investigate this question, our methodology consists of 3 steps. So first we extend the Lego model, then we formulate a standard transport problem, so a very easy way of representing this gas flows this blended gas flows in also linear formulation. And then we suggest something we call a blending transport problem, which is more sophisticated and considers more of the technical reality of this blending idea. And this is a mixed integer linear formulation. And last but not least, we want to evaluate our blending results from the standard transport problem case versus the blending transport problem case. And this is done based on regret, which we measure in hydrogen non-supply. So the first step is extending the Lego model. As a disclaimer, in this paper we are working with stylized system, and here you can see the stylized natural gas system. So first we introduce this system in terms of gas nodes and pipelines. The gas demand in the system is covered by natural gas wells. We also have long-term natural gas storage units and a natural gas demand there. Furthermore, we introduce hydrogen units. So the model has the option of either of building electrolyzer units. So this means converting power to hydrogen, or steam methane reforming, meaning conversion of natural gas to hydrogen, and short-term hydrogen storages. But we also include dedicated long-term hydrogen storages in order to see if they can foster the storage of hydrogen on an interseasonal basis. We also introduce dedicated hydrogen demand, and this is quite tricky since there are no time series for this as of today. So this includes a lot of assumptions. And last but not least, we introduced the option of blending, and blending considers the mode of hydrogen transportation, so blending in transmission, but also a share of the actual natural gas demand can be substituted by hydrogen, which is in this case by 10%. And we also consider co-firing of hydrogen and natural gas in gas-fired thermal units. So first done, we extended the Lego model. So now let's have a closer look at the formulation that we propose. So for example, if you want to keep your model a linear problem, then you could split this gas flow variable in a natural gas flow variable and a hydrogen flow variable. And then take a very simple approach by predetermining the share of the pipeline capacity there, and setting this as the bounds on the hydrogen flow and sparing it out for the natural gas flow. So this is a very easy and straightforward transport problem. However, this transport problem has two issues. First issue is that that gas flows other than power flows are subject to inertia. So power flows can change the direction instantaneously or almost instantaneously, whereas gas cannot. However, this formulation allows for this to happen. And the second issue is that actually blending means that you can blend up to a certain share of the actual natural gas flow. So if your flow is 50%, you can blend 10% of the 50%, but not 10% of the pipeline capacity. And this formulation does not consider that. And as a result, when you run your model and you look at the gas flows along one of the representative days, you end up with something like that, where gas flows, individual pipelines change their direction on an hourly basis, and this is not representative at all, at least when you want to look at an operational problem and figure out how your gas flows look. And also the other thing that this simple transport problem does allow for is that hydrogen flow and natural gas flow can go in opposite directions in the same pipe. And this is also not possible in reality since gas flow is a function or a result of the pressure gradient. So to overcome those issues, we propose this blending transport problem where, and just bear with me, I will go into more detail about the equations. So if we first have a look at those sets of equations, then we introduce this binary variable alpha, and by doing this, we achieve two things. First, we ensure that the flow direction of hydrogen and natural gas is in the same direction, and second of all, this alpha only is subject to representative days. So it's subject to one decision per representative day and does not allow the flow direction to change from 1 hour to the next hour. And this is also a very good representation of reality. So by doing this, we actually achieve, by imposing those equations, we actually achieve that the direction is ensured. However, the second issue I stated before is that we can only blend up to the level or a share of the level of the actual natural gas flow. So this is where we need those two additional constraints that ensure that, and also we have to include relaxation, and this is necessary to govern the negative flow direction of hydrogen, as otherwise this problem is ill-defined. And as a result, when we consider this formulation, our gas flows look much more reasonable, first of all, and we've overcome those issues. But now we come to the question, does this even matter, and what's the result or the impact in terms of our expansion planning decisions? So if you have a closer look at our results, we can see there the investment decisions in the power sector, which actually change if we switch from the simple to the blending formulation. This is represented here. So in terms of the total system cost, the effect.
£15. What do you mean when we tapped? I don't think it was on my bank statement yet, but.
Was that a question to Thomas, or? I think we might just have to mute someone, but yeah, go ahead.
Okay, so if we have a look at those investment decisions, here are just the investment decisions represented that actually change. In terms of the total system cost, that change is not so significant as it is only 0.5% of the total costs. However, in the net capacity, in terms of net capacity relocation, in the power system, almost 24% of all the capacity siting decisions change on a net basis, and this could present itself as being significant. If we have a look at the investment decisions in the hydrogen sector, we get a very similar result, and in this case, for example, for the electrolyzer units, almost 97% of siting decisions in terms of net capacity relocation are unchanged. So now we come to the question, does this matter in terms of feasibility of our expansion planning results? And in order to evaluate these questions, we evaluate the planning decisions from the simple case versus the blending case and investigate hydrogen non-supply. So let's talk about the quality of planning decisions. In order to do this, we fix our investment decisions from the standard transport problem case and run the blending transport problem case as an operational problem. Here we have three variables which are associated to costs, and they are very common in energy system models, and they represent kind of last resorts. So they represent energy non-supplied, meaning electricity, hydrogen non-supplied, and natural gas non-supplied. And we assign different costs to them. And we decide that energy non-supplied means the worst case. So we don't want the model to end up with energy non-supplied, but we assign the lowest cost to hydrogen non-supplied since we want to investigate this. And if we run this particular case, we end up with 7.25 million standard cubic meters of hydrogen non-supplied, and this corresponds to 2.6% of total hydrogen demand. However, since we have a variable hydrogen demand, since hydrogen can also substitute natural gas, this is the result, although hydrogen demand has already increased by 30 million standard cubic meters. So in terms of total system costs, if we omit these hydrogen non-supplied costs, since we might not have a clue about them at the moment, since this has not been established yet, we end up with total regret of 26 million euros, which is about 4% of total system costs. Coming back to the question, does this matter? Does the formulation matter? I would answer this question and say yes, it does, as we illustrated here. So what are the main conclusions and takeaways from this presentation? hydrogen is considered a cornerstone in the EU's energy policy. However, there is still a lot of uncertainty about where infrastructure should be built, how the actual mode of transportation should look like. Second of all, blending has been considered a valuable option to ramp up hydrogen. And third, the formulation of gas blending has to be considered at least to some detail, as otherwise you will end up with regretting your planning decisions. So that's it for my talk. Thank you very much for listening and joining in, and I'm looking forward to your questions.
Thanks, Thomas.